Now that you've seen how to write down an equilibrium constant expression, let me show you specifically how this works for acids and bases. So when you're talking about acids and bases, we're going to assume that if you're dealing with equilibrium, that we're looking at Bronsted-Lowry acids and bases. So just to refresh your memory about what a Bronsted-Lowry acid or a base is, okay, Bronsted-Lowry acid is a proton donor, a Bronsted-Lowry base is a proton acceptor. So we can write down an equilibrium reaction for a Bronsted-Lowry acid or for a Bronsted-Lowry base. So we're going to call the Bronsted-Lowry acid HA. If this comes into contact with water, the HA dissociates or breaks apart into H plus and A minus. And the H plus latches onto the water to make H3O plus or hydronium ions. We're going to use H plus and H3O plus interchangeably. And if I have a base, then that combines with water. Now the water dissociates or breaks apart into H plus and OH minus. And the proton from the water latches onto the base to make BH plus. So now that I have these equilibrium expressions, I can write down an equilibrium constant, right? Concentrations of the products divided by the concentrations of the reactants. So for Ka, which is for the acid, the products are H3O plus or H plus and A minus, right? The conjugate base of HA. So Ka is going to be H plus times A minus over HA. And then for the base, I have Kb. This is going to be the products over the reactants once again. Concentration of BH plus times the concentration of hydroxide ion divided by the concentration of the base. Notice that I ignore the H2O in both cases because water is a pure liquid and I only have to worry about aqueous solutions. So now when these reactions take place, there's going to be a certain order or preference for the reactions. Okay, and so the general rule of thumb is chemical reactions always go from stronger acids or bases to weaker acids or bases. So how do you know what's going to be a strong acid or what's going to be a strong base or a weak acid or a weak base? Well, there are different ways to quantify how strong the acids or the bases are. And one way to do it is by looking at the equilibrium constants. Okay? The problem is these Kas can be very, 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 very different from each other. Okay? Super, super, super strong acids might have Kas that are enormous, like 10 to the 10th or even greater. And super duper weak acids might have Kas that are really small, like 10 to the minus 10 or 10 to the minus 50 even, right? Even smaller than that. And so it becomes hard to compare things that are so vastly different from each other. Okay, and so what people do is they look at logarithms, right? The log has to do with basically the exponent. So we're going to call pKa the negative log of Ka, and pKb is the negative log of Kb. This is not the same as pH, right? Most people think of pH when they talk about acids or bases. The definition of pH is negative log of the concentration of H plus or negative log the concentration of H3O plus. Okay, and so pH does not have to be the same as pKa. Okay, you can have acids with very, for example, low pKa's, but maybe not so low pHs depending on the concentrations. Okay, the way I think about it is the pH of the solution has to do with how concentrated it is. Okay, you could always change the pH of a solution by making it more or less concentrated, but I can't change the pKa. That's like a physical property. Okay, pKa's are whatever they are. Okay, and so what I want to show you here in this table is the relationship between the strength of an acid and the strength of the conjugate base. At the top of the list are very, very strong acids. These are things that dissociate nearly 100%. So things like perchloric acid, sulfuric acid, okay, mineral acids, HI, HBr, HCl, nitric acid. These will completely dissociate in water. Now, there's an inverse relationship between the strength of the acid and the strength of the conjugate base. So even though perchloric acid is a super strong acid, the ClO4 minus ion, right, the perchlorine ion, is going to be a very, very weak conjugate base. Okay, so the stronger the acid, the weaker the conjugate base. And if you scroll down here, for example, to the bottom, you can have something like hydrogen gas or ammonia or methane. These are super weak acids, right, dissociate very, very, very little in water, but the conjugate bases of these things are super, super strong. Okay, so for example, the amide ion, or the hydride ion, or the methite ion, which are NH2 minus, H minus, and CH3 minus, these are incredibly strong bases, even stronger than what you might be used to in terms of thinking about in like a conventional sense. Okay, just as a reference point, here's the hydronium ion, and here's the hydroxide ion. Okay, and so all of these things on the bottom, like NH2 minus, H minus, CH3 minus, are actually even stronger bases than hydroxide ions. Okay, and so OH minus is not the world's strongest base. Okay, when you learn about organic chemistry perhaps later, you'll see that there are other substances that are even stronger bases than hydroxide ion. Similarly, hydronium ion is not the world's strongest acid. Okay, there are things that are even more acidic than H3O+. Okay, all those things at the top of the list.